Hi, everyone, and welcome to another seminar at Physics Latam. Today, we are happy to have us Professor Natalie Paquette. Professor Paquette is now a professor at University of Washington. She earned her PhD from Stanford University and completed her postdoc research at Caltech and IAS. Professor Paquette's expertise lies in string theory and quantum field theory, particularly at their intersection with modern mathematics, as we will see in this talk. Currently, she is a DOE Early Career Research Fellow and serves as a principal investigator and executive committee member of Simon's collaboration on celestial holography, a new collaboration which became recently very famous for getting an $8 million grant. Additionally, she's a visiting fellow at the Perimeter Institute for Theoretical Physics. Today, she's giving a talk on twists of supersymmetric theory applications. If you have any questions, please do not hesitate to ask. Now I leave with Natalie. Please go ahead. Thanks for accepting our invitation.
Thanks so much. That was a really great introduction, and thanks to all of you for coming. So as you heard today, I want to talk about twisting supersymmetric theories, what that means, how to do it, and hopefully by the end of this lecture, you will have the tools that you'll need to do further reading on the topic if you're interested, particularly as it applies to holographic situations. And yeah, feel free to interrupt me with questions as you have them. Okay, so what I'm going to tell you about today is based mostly on some TASI lectures that I wrote up. Well, I gave the lectures in 2021, and I did a write-up of them with Nicholas Garner. And additionally, of course, there's a lot of references cited in the TASI lectures that can give further details on everything that I'm going to talk about. So what's the basic idea of what I want to tell you about today? So you all have been studying holography this term, probably from various perspectives, and you've learned that outside of some special techniques like integrability or maybe other special methods that you've been using for some of these systems, it's difficult to generically to compute generic observables in strongly coupled field theories. Like, for example, the conformal field theories that are dual to weakly curved Einstein gravity in the bulk of ADS-CFT. You probably learned how the strong coupling is useful for the emergence of large radius gravity duals and so on. So because of the difficulty of computing something in a generic strongly coupled field theory, a priori, it can be hard to test richer facets of dualities beyond just matching symmetries or certain things. Of course, we have more tests of the ADS-CFT correspondence than just symmetries. We have many more things. And one of the very useful tools in this context arises when the theory that you're studying has some additional symmetry. In particular, the focus of this lectures will be on additional supersymmetry. So we're going to use an additional symmetry, supersymmetry, in this theory, in these theories. And it will turn out that if you have supersymmetry in the game, there are a special class of observables, not generic, but a special class of observables, that are computable and have various nice properties, and also beautiful connections to math, but I won't say too much mathematical stuff in this talk, that are computable and have various nice properties. So that enables you to test things on both sides of a supersymmetric duality, at least of the level of these special observables, which are often called protected observables. So these observables are called protected, or more generally BPS. And that just means they preserve some fraction of the underlying supersymmetry that the theory has. And different kinds of BPS quantities will preserve generically different fractions. Okay. So the main question that we'd like to ask is, can we, and if we can, how, extract a simpler theory from the original strongly coupled theory we started with that contains only information about these BPS observables and lets us just work with them directly and compute everything we can. That contains only information about the BPS quantities. And that procedure is what's called a twist. So that's what I'm going to spend most of today telling you about. So the answer, which we're going to develop today, is that there's a procedure called a twist or a supersymmetric twist that will let us extract precisely these BPS or special quantities from a generic strongly coupled theory. Now, the twist is useful. Mostly, I'll talk about twists at the level of field theory. So you should, if you're interested in holography, you should think of this as something that I'm doing on the boundary field theory side, in particular, just because that side is much more rigorously developed, and it's a lot easier to give a pedagogical lecture about the field theory side. But in principle, everything you want to do to the boundary of an ADS-CFT dual pair, there should be some analogous dual prescription that you can do in the bulk as well, so that there's some notion of a boundary twist and some corresponding notion of a bulk twist. And ideally, you'd like to do things on both sides and compare them, or if one side is harder than the other, the hope is to, as usual, glean some information about the more difficult side from the more tractable side. So this idea that a twist is something that you can perform not just on a supersymmetric field theory, but also on its putative bulk dual, leads to the notion of what's called twisted holography, which has been my motivation for studying a lot of these things in recent years. So I won't be able to give a full, complete lecture on twisted holography. I'll mostly tell you about twisting supersymmetric field theories, so kind of what happens on the boundary half of things. But I will say a few motivating words about it occasionally. And twisted holography, in particular, is a subject in recent years that's been developed by Costello in collaboration with C. Lee and Davide Gaiotto and myself in various papers. And many other people have contributed to it, so I'm not giving an exhaustive list right now, of course. But again, the idea of twisted holography is that we want to study the ADS-CFT correspondence for supersymmetric top-down examples. Top-down meaning constructions that arise from string theory, for example, the classic duality between 4D equals 4 super Yang mills and type 2B on ADS5 cross S5, and so on, at the level of these BPS quantities. So making things as precise as we can for the most generic kind of BPS observable. And this is most interesting and most rich when we focus on twists that use or preserve the smallest possible fraction of the supersymmetry. So as I'll tell you about, there's a variety of different kinds of twists preserving different fractions. Things like half BPS states, which preserve half of the underlying supersymmetry, that's a lot of the supersymmetry. Those have been studied in great detail using many other methods for many, many years, but things have started to acquire new life and become more interesting as we've learned about different enrichments of these kinds of twists that preserve fewer and fewer of the underlying supercharges. And so things are still being developed on that front, even though BPS, studying BPS quantities is something that people have done for a very long time, since the beginning of the ADS-CFT correspondence, and of course, from the earliest days of just supersymmetry. So today, with that motivation in the back of our minds, what we're going to do is focus mostly on the field theory side. Which if you're a holographer, you can think of as the boundary. And twisting is rigorously established for supersymmetric field theories. There are conjectures for what it means on the bulk side. How can you twist string theory or M theory, or even just the supergravity theories that are their low energy approximations. So in the bulk, twists are more conjectural. Their status is more conjectural. The initial proposal was by Costello and Lee. There are now partial proofs, in fact, of this conjecture by Saberi and Williams. So we have very, very good reason to believe these conjectures, and things seem to work spectacularly well in many interesting examples that have been studied by Costello and Gaiotto and myself and other people. But I'll just tell you the punchline. The main idea of the conjectures is that they believe that these suitably defined twists of the bulk theories become what are called topological string theories. Or often more concretely called the A and B models. And topological string theories have also been studied for a long time and are known to capture supersymmetric quantities in full physical string theories. And so it's expected that these kinds of special subsectors of string theory also play an important role in the twisted holography stories. Okay, so that's all kind of the general story and motivation. Are there any questions about that before I get into the proper lecture? Any questions about anything I've said or where I want to go? Okay, so far so good. All right. So for most of the lectures, I want to tell you about what a twist is, what are its properties, and how you can compute it. So let me start out with a useful analogy, which has all of the formal similarities, many formal similarities, at least, to a twist, closely related to the subject of twisting, but that you might have already learned about previously in other contexts. And that's BRST quantization of gauge theories. More generally, you can work with an extension of this called the BV-BRST formalism. That's useful not only in gauge theories, but also is essential in studying things like string field theory, which has a lot of interest lately, and so on. Working with this kind of big BV-BRST type structure it's something that is often essential, especially when working with, say, the bulk side of these twisted holographic dualities, really working with topological string theories proper. But that would be a lecture series in its own right, so I'm mostly going to sweep it under the rug, but it's something you should have in the back of your mind as an important piece of formalism in string theory and in twisted holography. But let's focus on kind of its perhaps hopefully more familiar version, just BRST quantization of ordinary gauge theories, and see what this analogy can tell us about twisting. So let's recall what happens when we're quantizing, say, ordinary non-abelian gauge theory. Well, what do we do when we do BRST quantization of ordinary gauge theory? We augment the space of fields by the Fadeev-Popov ghosts, which are usually called the B and C ghosts. And we also have a Lagrange multiplier field, which typically we can just integrate out directly in the path integral. And the idea is that we augment the space of fields using these extra ingredients precisely in order to gauge fix our path integral. So what we do is we deal now schematically with the bigger path integral. We still have our functional integration over the gauge field A, but now we have an additional Lagrange multiplier field B, whose role in life is to implement the gauge fixing condition that we choose. It's the Lagrange multiplier field for that. And we also have some additional ghosts, the B and C ghosts. And so our action becomes a sum of our original Yang-Mills action plus this term where you have the Lagrange multiplier field multiplying some functional or some gauge fixing functional that I'm calling f of a, which we choose. For example, it could be like del mu a mu equals 0, the usual covariant gauge, but in general, you have freedom to choose your gauge fixing as you like. And then there's the term coming from the B and C ghosts, which comes from taking the derivative of that functional with respect to some gauge parameter A and kind of replacing that gauge variation parameter with the C ghost. Okay, so we do that. You might remember that we do all of this because everything I've just written is a simple re-expression of the gauge fixed path integral. You know, we had dA, we wanted to insert some delta function, f of a, which localizes us on that gauge slice that we're trying to fix. The Faddeev-Popov determinant from whence the ghosts come is kind of just that Jacobian factor. And there's my original action. So this enlarged space of fields just comes from manipulations to re-express the gauge fixed path integral, as you've probably seen before. And the important point is that for this gauge fixed path integral in this extended space of fields, well, we fixed our gauge symmetry. So we no longer have gauge symmetry in the game, but in the BRST quantization, what we have is a new emergent global symmetry called the BRST symmetry. And this is a fermionic global symmetry. It ends up essentially replacing what used to be a gauge symmetry and trading it for this interesting global symmetry that we can work with. So just to remind you, how does the BRST symmetry act on the space of fields in our theory? The details aren't important for this lecture, but hopefully just to get some bells ringing and remind you of some hopefully familiar things. The BRST variation acts on our original gauge field well, essentially just like the gauge transformations, the original gauge symmetry that we had in the game. But now our gauge parameter, if our old gauge transformation was called zeta of x, that's now effectively been replaced by our C ghost field. And I've included another constant parameter epsilon, which is Grassmann odd, because C is also a Grassmann odd field, as you probably remember, and odd times odd is even. So it amounts to essentially the original gauge symmetry that we started with. The Lagrange multiplier field is just invariant under the BRST transformation. The B ghost transforms like this. And finally, the C ghost basically transforms like an adjoint matter field in our theory, but with the funny statistics properties that you probably remember from the ghosts. They're like anti-commuting scalars. And once you have this kind of the symmetry, you can do your usual thing and build a Noether current for the symmetry called the BRST current and construct also a corresponding charge. And I'm going to call this fermionic BRST charge QB. And in particular, because the BRST charge is fermionic, as you may remember, it has the property that it squares to 0. And that's just because, well, if it's fermionic, then its anti-commutator should just vanish. So anytime we have a fermionic global symmetry, that the corresponding symmetry generator is going to be nilpotent, which just means that if you act with it twice, it'll be 0. Okay. Any questions about that? Is that familiar so far? So the key point, which we're also going to see again shortly in the context of supersymmetric theories, is that any such fermionic nilpotent operator is useful because we can study what's called its cohomology. That's also what we do when we BRST quantize. And in the BRST context, we identify our physical Hilbert space with the cohomology with respect to this BRST charge. So I'll say what the cohomology is. So here, Hx is my extended field space. So it's the thing that includes the gauge fields, the ghosts, all of this extra stuff I added in by hand. It's often sometimes called the BRST complex. And what this notation means is that I have to take kernel of QB mod image of QB. I'll also define that in a second if you've never seen it before. In words, we take things which are invariant under the BRST charge, BRST invariance, but we perform an equivalence, or we quotient out by things which are BRST invariant in a trivial way. So the kernel of the BRST charge, I'm putting a hat on it just to emphasize that it can act as an operator on the local observables in my theory. If I have some state psi that's in my extended Hilbert space, again, including the gauge fields and the ghosts and everything else, well, in the kernel just means that it's annihilated by QB hat. And we say that such things are BRST closed. That's just the terminology. And then the image is if we have two such states in our large extended Hilbert space, if something is in the image, is if psi is in the image, if it is in the form of QB times something, QB times some other state psi. And then we say that in that case, psi is QB exact or QB trivial, BRST exact or BRST trivial. And indeed, something of this form is definitely going to be annihilated by the BRST charge, just because if we act on it with the BRST charge, the property that the BRST charge is nilpotent, it squares to 0, means that psi would get automatically annihilated if it's in the image of the BRST charge. So it is BRST closed, but sort of in a trivial way. And we want to remove or mod out or kind of identify states which are trivial. They're not interesting. In other words, BRST quantization is just an instruction to keep only the states that are annihilated by QB or the QB closed states. But we identify two states, psi and psi prime, if they differ by something QB exact. So psi and psi prime are physically distinct. About that?
If there is any question in the chat, I will let you know.
Okay. So psi and psi prime are indistinguishable in cohomology. That's all we're doing here. Okay. And you might wonder why we mod out by these QB exact states. And in fact, it's quite a natural thing to do, because if you just consider the inner product of psi with some other exact state that I'll write as QB chi again, well, because psi by definition is a QB closed state, so I'm considering psi that are annihilated, they survive in our BRST cohomology. Then if I just do this, I can see that the inner product is automatically 0. So all QB exact states are orthogonal to any other BRST closed states, what we identify as the physical Hilbert space. So since the overlap between QB exact states with anything else that survives in cohomology is 0, it's also, it is well defined to perform this equivalence relation and effectively get rid of them or ignore them. Okay. Great. So, as you guys probably remember, when you take this cohomology of our extended Hilbert space by the BRST differential, you land precisely on what were just the gauge invariant observables or operators or states, depending on how you which picture you want to work in, gauge invariant physical states in the original theory. So in particular, even though we added all these, for example, ghost fields by hand, the B and C ghosts, nothing, there are no states or equivalently operators in cohomology that survive that have a non-zero ghost number, that have these B and C ghosts involved. They're very useful for implementing the restriction to these gauge invariant observables, but they themselves don't survive. And that's good because they were something that they're auxiliary fields used to implement gauge fixing, so they shouldn't appear in physical states. And that's probably what you remember from your QFT class as well. Okay. Any questions about that? Hopefully familiar to most of you. Okay, so BRST cohomology has various consequences, various desirable formal consequences. And again, I say these things at the level of a review, because if you understand this, you'll understand supersymmetric twisting pretty much immediately. So if these arguments are comfortable and familiar to you, then twisting should also make you pretty happy, which we'll get to shortly. So there's a desirable formal consequence of working in this BRST cohomology. For example, if we think about the gauge fixing part of the action, the part that includes the Lagrange multiplier field and the B and C ghosts, so this thing that schematically is like this that I wrote down before. First of all, one should note that it itself is QB of something. In particular, B times my gauge fixing functional F, although the details aren't so important for us. So because of this property, which is not so hard to show once you have the BRST transformation laws, if we wanted, say, to change our gauge fixing conditions slightly from our original functional F to some slightly deformed functional F tilde, which is like the original F plus some infinitesimal variation, then, well, ideally nothing physical would change if we're doing if this procedure is persistent, because the gauge fixing functional is just something we choose. We should have the freedom to move it a little bit and not affect any physical observables if this BRST procedure is well defined. So supposing we make such a small transformation of our gauge fixing condition, then the action changes. It picks up it goes from S to delta S. The only part that changes is the gauge fixing part of the action. And that, remember, was just QB of something. Oops. In the variation, it'll be B delta F. And so under such an infinitesimal variation of our gauge fixing conditions, any kind of physical quantity, for example, an amplitude that transitions between two physical states, will be basically immediately invariant under this kind of transformation by BRST exactness of the charge. So for example, if we're considering like some transition amplitude between an initial and final state, we could also go to Euclidean signature and consider correlation functions. Even a Lorentzian signature, we could consider correlation functions, your favorite observable. But let's say I have an initial and final state psi I and psi F. Well, if they're physical states, then by definition, they have to be non-trivial in BRST cohomology and closed, so QB annihilates them. And then any kind of amplitude, say between psi I to psi F, has to be invariant under this change. So the variation of such an amplitude, here I'll just write some general unitary operator taking us from psi I to psi F. In the path integral formalism, well, I'll have everything I had before, but now I'll insert the states in their wave functional form. E to the IS, QB, And the variation brings down that QB term, and then I have psi I. But if I remember the fact, well, first of all, the action is BRST invariant. That's how we found the BRST symmetry. Moreover, psi F and psi I are BRST closed. They're annihilated by the action of that supercharge. So I can just pull that BRST charge through everything in my path integral. And then I immediately get 0 because the BRST charge should just be viewed as a total. I get something that's a total derivative in field space. The BRST charge acts as like a functional derivative in field space. So you should think of QB as like a derivative acting in space of fields. And so I have something that in essence is purely a boundary term in field space and should be 0 provided nothing funky happens at infinity, which I'll always assume. So this working in BRST cohomology gives you invariance under things that you should have invariances under, and that takes the form in particular of BRST exactness in terms of this form. So as you, again, just to kind of recap, BRST ended up being a very clever way by expanding the space of fields and working in this cohomology to compute what would be a very complicated infinite dimensional quotient. Namely, it's an infinite dimensional quotient of our original theory by this infinite dimensional group of gauge transformations. All transformations of the form zeta x, where zeta is g valued and, it's some arbitrary space function. And this kind of trick of kind of making your space of fields bigger and then restricting it back down using cohomology to get the original quotient that you wanted in the first place, that's very common in mathematics. And the formalism can be developed further and in greater generality for things like string theories and so on. So we enlarged the space of fields with these free anti-commuting ghosts. We obtained a nilpotent symmetry which acts on those fields, and the cohomology with respect to that fermionic nilpotent symmetry, global symmetry, was precisely the quotient we want. Just a bit of terminology that you might see in kind of the twisting literature in general. If all we care about is things at the level of cohomology, like physically, those are our gauge invariant observables at the end of the day that we want to compute, then in principle, there can actually be many ways to enlarge the space of fields. But all of them can in principle be okay or useful, provided they give us the same cohomology back. So this notion in mathematics is called a quasi-isomorphism, which just a quasi-isomorphism is going to be a map between these enlarged spaces of fields and the symmetry generators, which in mathematical terms will be called a differential. That is an isomorphism at the level of cohomology. So in BRST and also more generally in twisting, typically you can work at the level of quasi-isomorphism, kind of choose whichever bigger space of fields and differential is the most useful to you, provided at the end of the day you get back the cohomology that you want. So that terminology is pretty common. Okay, so all of that was review, but now we're just going to use the same considerations, the same formal types of structures, and really twist a supersymmetric field theory. So supersymmetry, a supersymmetry algebra, is just a fermionic extension of the Poincare symmetry, or in the context of holography, it could be actually a fermionic extension of the full conformal symmetry, where you have additional anti-commuting generators called supercharges. And if you haven't heard of SUSY before, because I have a fermionic supercharge, if I act with such a fermionic thing on a bosonic thing, I'll get a fermion and vice versa. So it's something that's swapping bosons and fermions and having them symmetric in your theory. And a twist is nothing but an instruction to take the cohomology of a different fermionic global symmetry. Namely, instead of using the BRST charge, take the cohomology of some supercharge Q in your supersymmetry algebra. That's really all it is. Of course, I'll unpack that a lot more in the lectures, but you should really have in your mind just the BRST formalism, and you'll already kind of understand most things about what it means to twist a supersymmetric field theory. Okay. Let me introduce a little bit of notation that I'll use in the rest of these lectures, because it's just very convenient when talking about supersymmetric field theories. From now on, if I have the commutator between two operators A and B, I'm going to mean it in the sense of what's called a graded commutator, which just means it's going to be either a commutator or an anti-commutator, depending on the fermion parity of the operators there. It's just a way for me to only draw angle brackets, or only draw square brackets rather than worrying about square versus angle brackets. So Fa and Fb are the fermion parity of the operators A and B. So if they're both fermions, it becomes an anti-commutator. Otherwise, it's the ordinary commutator. So that's just a convenient way for me to write my brackets. And again, it's very common in a lot of the literature. So for example, I would write the BRST charge anti-commuting to 0 in just this way, with the understanding that it's a graded commutator. Okay. So am I right in saying that you guys haven't had supersymmetry yet in your lectures? Like, this isn't a topic you've necessarily seen before?
Well, I'm not sure, because we already organized a mini course in supersymmetry, so I think.
Okay, so maybe
But I
some
don't
have
know.
seen it and some haven't.
Yes, exactly.
Okay. Well, yeah, there shouldn't be any background in SUSY required, but if you have it, then yeah, even better. But let me just write down some example supersymmetry algebras. In my graded commutator notation. So for example, kind of the most basic supersymmetry algebra, and if you've studied SUSY, you've seen this before, it's what's called the 4D n=1 supersymmetry algebra. It's kind of the minimal amount of supersymmetry you can have in 4D. And there's just an extension of the ordinary point Gray algebra that you started with by additional fermionic generators, Q alpha, and its Hermitian adjoint, Q bar beta. And again, both are fermionic, and they anti-commute up to these kind of familiar sigma matrices to the generators of space-time translations, P sigma. And again, in the graded notation, you know, these you should think of as the anti-commutators, and this is an ordinary commutator, but in the graded notation, it all looks the same. So the minimal amount of supersymmetry you can have in 4 dimensions is just the extension by Q alpha and Q bar beta, where both of them carry ordinary Lorentz spinor indices, alpha or beta dot for the conjugate. Another important, kind of even easier example is the minimal supersymmetry algebra necessary to have supersymmetric quantum mechanics. And there you just have, again, just one single supercharge Q, obviously no interesting space-time indices for quantum mechanics, and its Hermitian adjoint Q dagger, and they anti-commute to the Hamiltonian of your quantum mechanics theory. That's what it means to have a supersymmetric extension. And all other commutators or anti-commutators are 0. For example, the supercharges commute with the Hamiltonian, and also Q commutes with itself, or anti-commutes with itself, and Q dagger likewise. And something you can immediately notice right away in this nice, simple quantum mechanics example is if you consider the expectation value of the commutator of Q and Q dagger in the vacuum. Well, I can expand this out and write it as Q dagger Q plus Q dagger. And both of these are just the sums of manifestly positive quantities. These are now inner products, so they're manifestly positive. So I have something that's greater than or equal to 0. But of course, the commutator of Q and Q dagger is the Hamiltonian, which immediately tells us that the spectrum of the Hamiltonian is bounded from below, and the minimal energy state is the ground state. It's precisely 0. And that's quite a departure from non-supersymmetric theories, where normally we can shift the 0 of the potential in SUSY quantum mechanics pretty much however we like. But in supersymmetric theories, we're fixed to have the lowest energy state, the ground state, or the vacuum sit at precisely 0 energy. And supersymmetry breaking would happen if we found a non-zero vacuum energy, like we have in our universe. Okay. So let me introduce one more supersymmetry algebra, which is non-minimal, meaning it has more than the lowest number of possible supercharges that you have in this extension to the Poincare algebra. I'm going to use this particular supersymmetry algebra as my working example for the rest of the lecture. Anytime I have to do something, I'll work in this algebra, in part because it's pedagogically a bit simple, but also because it has close connections to the topological string theories that I mentioned earlier, and has kind of a long history of connections with math and twisted holography and other things. So a non-minimal supersymmetry algebra that I'm going to work with a bunch today is what's called the 2D 2,2 SUSY algebra, where the minimal supersymmetry algebra, by contrast, would just have one supercharge. Okay, so what's the notation? Well, the notation just means that I have 2 chiral, or in Euclidean signature, holomorphic supercharges, and 2 antichiral, or anti-holomorphic supercharges. So 2 each. So for example, if I wanted to write the supersymmetry algebra in Lorentz signature, let me define space-time coordinates x plus and minus to be these linear combinations of my space and time, x0 and x1. And in Lorentz signature, my SUSY algebra would look like so. The only interesting non-vanishing anti-commutator that I need, as usual, it's between the supercharges and their Hermitian adjoints. And again, they anti-commute to translations in particular space-time directions, in this case, to the 2 kind of light cone directions that I've defined. In these lectures, I'll often work in Euclidean signature, where twisting is a little bit more natural and also better defined. And so if I pass to Euclidean signature, then the x plus coordinate becomes z bar. The x minus coordinate becomes minus z. So I'm just treating my 2D spacetime now as a Euclidean complex manifold with complex coordinates z and z bar, which are complex conjugates of each other. And in that case, q plus and q bar plus anti-commute to a translation in the anti-holomorphic direction, and q minus and q bar minus anti-commute to translations in the holomorphic direction. Okay. An important feature of non-minimal supersymmetry algebras like the one that I just wrote down is that there can be additional bosonic symmetries that act non-trivially by rotating the fermionic generators amongst themselves. But of course, they don't touch the Poincare algebra, that's still there. But if you have more supercharges, more and more supercharges, there can be bosonic symmetries that rotate them, and that'll further enhance the supersymmetry algebra. So these further bosonic symmetries are called R symmetries. It's called the R symmetry of your supersymmetric algebra. So in this example, the R symmetry group, which again is bosonic and I'll denote by G sub R, is given by a product of 2 U1 symmetries, which I'll call the U1 vector and the U1 axial by analogy with the vector and axial symmetries that you've probably seen in 4D QFT. So I'll denote their generators by R sub V and R sub A, and they act as follows on the supercharges. So the vector symmetry acts on the two chiral supercharges with charge +1, and its conjugates, their conjugates with charge -1, whereas the axial symmetry acts like so. With those plus and minus charges. There are also kind of the usual discrete symmetries, the discrete spacetime symmetries that can act on the supersymmetry algebra. Parity, in this case, will reverse plus and minus, the plus and minus subscripts on the two supercharges, and charge conjugation will take q plus or minus to q bar plus or minus its conjugate. But other than that, those are all the symmetries that we have in the game, all the symmetries that we need. If I studied, for example, an even less minimal SUSY example, like with 4 chiral and 4 antichiral supercharges, I would find a larger R symmetry group, in that case, SU2 cross SU2, and so on. Okay, so now that we have all of those supersymmetry algebras kind of ready to go, given some supersymmetry algebra, given some supersymmetry theory with its associated superalgebra, what is the twist? So as I said, in the sense of the word that's become standard in modern terminology, a twist really just means an instruction to take cohomology with respect to any nilpotent supercharge in the algebra. I'll tell you what it meant historically and why that's a little bit less general than what twisting means nowadays. So a twist is cohomology with respect to any choice of nilpotent supercharge in your algebra that you want. And in general, there are many such choices. So that means in a twist of some supersymmetric theory, you study operators that are Q-closed. So previously, I just written Q annihilating states. Often I like to work with local operators instead of with states, so I'll write the action of Q and O like that. Again, Q is annihilating the Q-closed local operators. So we say that such things are, if you like, BPS with respect to that supercharge Q, meaning they preserve some of the underlying supersymmetry that generated by the supercharge Q, at least in particular. And moreover, I'm also going to assume throughout these lectures that SUSY is not spontaneously broken. So I'm doing a twist of a theory such that the vacuum is also preserved by that supercharge. That's my assumption. Once you do that, once you restrict to Q-closed things, and you assume that there's no spontaneous supersymmetry breaking, then it immediately follows that correlation functions of Q-closed operators are invariant under Q-exact deformations, similar to what we saw in the BRST case, and that follows immediately. So in particular, if I have Q-closed operators O, maybe I'll deform one of them by some Q-exact deformation. Remember, I'm using graded commutators here. Then a correlation function, say in Euclidean signature, where it's easiest to work with these things. Well, let's say I have O and the dot dot dots indicate a bunch of other Q-closed operators. Now I've just deformed O by some extra Q-exact term. That's the original correlation function plus this new term that I've added, which of course, this is just Q lambda plus or minus Q lambda, depending on the parity. But now, because I'm in a correlation function with only Q-closed operators, I can commute or anti-commute Q past everything else and precisely have it hit the vacuum on both sides. So I can commute Q past any Q-closed operators without any penalty or picking up any extra terms. Q will act on the vacuum on the left and the right. And by assumption, since SUSY is not broken, it will annihilate the vacuum. And so the second term is just going to be 0 immediately. So therefore, at the level at least of correlation functions of local operators, once you start thinking about Q-closed things only, it's natural and in fact immediate to quotient by Q-exact operators. So Q-exact operators in such correlation functions, in correlation functions of Q-closed things, give 0. And so indeed, Q cohomology. If you want to focus on things that are BPS with respect to some supercharged Q, Q cohomology is the natural structure that comes out. Any questions about that? Okay. So let me say a little, oops. I almost got logged out of Zoom because of institutional like limits on how long I could be logged into Zoom. Hopefully I'm still there. Okay, let me say one more thing and then I'll pause for a break after that. Does that sound good? Yeah, the algebra of local operators will get cut down to a much smaller subset. It will become, you'll localize to a subalgebra of BPS operators that are annihilated by that supercharge. So it really is basically just taking you down to a subsector of the observables.
Okay.
So in other words, your algebra of local operators in your supersymmetric field theory gets much, much smaller, essentially. That's one of the reasons why twisting is a big simplification. If you force yourself to look only at things that are annihilated by some supercharge, well, the space of those local operators will be much smaller. Did that answer your question?
Yep.
So, as I said, twisting comes from taking the cohomology with respect to any choice of nilpotent supercharge that you have in your algebra. And in general, there are many such choices, and they give interesting and different results. So one thing to say immediately is that you can study and classify the space of all nilpotent supercharges in a given superalgebra. And that's called the nilpotence variety. Fancy name. That classification has been done, and you can read more about it in papers by Elliott, Safronov, and Williams. There's also a nice, more physics-oriented paper. The first one is more mathy, by Eager, Saberi, and Volker. So this classification has been done. You can look up all possible nilpotent supercharges for any supersymmetry algebra that you're interested in. How is that defined, or how can we find such a variety? Well, for a general superalgebra, we have, let me say, capital N supercharges, depending on which algebra we're studying. So I'm going to call them QI, I ranging from 1 to capital N. And here I is a kind of composite index. I'm combining my spinorial index, if applicable, with any R symmetry index that I might have if I'm working with an extended super algebra. And so in general, the brackets QI and QJ will take a form that looks like this for some suitable coefficients gamma. So the different QIs and QJs will always anti-commute to some suitable linear combination of translation generators in your superalgebra. And so, for example, if you want to take some general arbitrary linear combination of any of your supercharges with some coefficients QI, such that these are not all 0, then the requirement that whatever that supercharge is, the requirement that you want it to be nilpotent translates to some equations in gammas, QI and QJ, where mu is, of course, 1 all the way up to however many space-time dimensions you have, 1 to d. So you have d quadratic equations in these coefficients Q. And these quadratic equations are carving out the space of possible nilpotent supercharges. And that's what's called the nilpotence variety. And again, you can look up all of the possibilities. For those of you that have some geometry background and like it, I'll just remark that if Q is nilpotent, as we require, then if I scale up Q by any non-zero complex number, well, of course, that's still nilpotent. So generically, we want to quotient out by those possible scalings because they don't give us different nilpotent supercharge if we just multiply by some non-zero complex number. So the nilpotence variety defined by these quadratic equations is a subvariety of capital N minus 1 dimensional complex projective space. Projective space, where we quotientify those scalars. That gives nice geometric interpretations. Let me just tell you what we get more particularly in the case of our 2D n equals 2, 2 algebra. That'll tell us the kind of twists that we're going to be allowed to do. So in this case, I want to consider some generic supercharge Q. So it can have some coefficients Q alpha, where alpha is going between plus and minus, two-dimensional, and some other coefficients Q bar alpha multiplying the Q bars. And I want to solve for when this Q squares to 0. And this is a pretty easy exercise that you guys can check in a couple lines. But the nilpotence breaks down to the requirement that just Q plus times Q bar plus equals 0, and Q minus Q bar minus equals 0. Those are the equations that fall out from demanding nilpotence of that general supercharge. And that tells us that there are 3 non-trivial options for twists that we can have, at least up to equivalent options after acting by parity and charge conjugation. So only 3 inequivalent options for the twist. So let me use some of that freedom, take Q bar plus equal to 1 for convention. And again, I'm using kind of my rescalings to fix the non-zero value of Q bar plus at 1. The important thing is that it's non-zero, but I can use scaling, just fix the length to 1. Well, that tells us that Q plus equals 0. And again, this is a starting point that I'm just choosing by convention. I'm choosing Q bar plus to be the non-zero one, but any other equivalent choices are just related by charge conjugation and parity. So then there are 3 options given the starting point to satisfy the nilpotence equations. I could either have Q bar minus and Q minus both equal to 0. In that case, the nilpotence supercharge is just Q bar plus itself. I could have Q bar minus equal to 0, but Q minus non-zero. And then Q can be written as Q bar plus plus Q minus. Or I could have Q bar minus non-zero and Q minus equal to 0. I'll call this supercharge QA and this one QB. And then I have Q bar plus plus Q bar minus. So these are the 3 inequivalent possibilities for twists. The first one is what's called the half twist, and it was studied by Witten, Kapustin, and various others. The second twist is called the A twist, and the third is called the B twist. And after the break, we will explore some of the properties that these different twists have. Okay, so we had just classified these 3 possible twists that we can have for our 2D 2, 2 algebra. What are the consequences of having done this kind of twist? I'm going to tell you the immediate and most important consequences of taking one of any of these 3 twists. So we know we're taking a cohomology with respect to either Q bar plus, the half twist, or QA or QB. The 3 of them have different properties. So for now, let me suppose I work in flat space and Euclidean signature. I'm going to restrict myself to that setting for the moment. For our chosen supercharge Q, the supersymmetry algebra is always going to contain commutators that I'm going to schematically write like this. No matter which supercharge it is, Q is going to anti-commute with some of the other supercharges to certain translations in spacetime, certain linear combinations of the derivatives in general. Meaning some spacetime translations will always be Q exact in the image of Q, just right from the superpoint Poincare algebra. And that means that translations with respect to those particular space-time directions are going to be trivial in the twisted theory. In particular, correlation functions are going to be invariant under translations of any of the local operators in those directions. So explicitly, if we have a correlation function of Q-closed operators, operators that survive in the twist, and we wanted to consider a translation by one of these Q-exact translations del mu, say O of X plus some other stuff, well, that's just equal to, well, I can use the supersymmetry algebra to re-express the action of the derivative as Q, comma, Q mu acting on the operator O with whatever other insertions are there. But again, I'm doing correlation functions in the twist, meaning these correlation functions should only have Q closed observables in them, and therefore I can take that outside Q bracket and drag it past all of the other operators and enclose them. And then I can use the same argument that I did before the break and expand that anti-commutator or commutator, have Q act on the vacuum, and again annihilate it. So in other words, the correlation functions, at least locally, are constant in that associated space-time direction, x mu. The operator insertions in those directions are not part of, well, they're trivial in cohomology. We don't have to worry about the dependence of the correlation functions on those operators with respect to those space-time directions. So no dependence. The correlation functions have no dependence on the coordinates in those particular x mu directions. And well, as we know, the classification of these twists has been done. So for any given supersymmetry algebra and then any choice of nilpotent supercharge, we can read off which of the space-time directions actually got trivialized. How will our algebra simplify if the operators no longer depend on these particular directions? And the classification of these twists tells us that the trivialized translations, the ones that go away in Q cohomology, are of two basic types, always. Basic types. Well, I could either be trivializing just some single direction, so associated to the generators P mu. Let's say maybe some twist trivializes n of them out of my D total spacetime translations, or complex combinations of directions can also get trivialized depending on the twist. For example, the directions corresponding to translations by PA bar, which I'll write as the following complex combination. So for spacetime dimension D, in general, I'll have a general twist will be some mix of these two options. Some of the directions will be completely trivialized. Others will only be trivialized in terms of the anti-holomorphic coordinates, the z bars, but not the z's. So this is what is bound to happen in the twist. So Q cohomology is insensitive to translations along x mu and anti-holomorphic translations along the z bar a bars, which were just complex combinations of some of my original coordinates. So I've written the most generic case where you have a mix of both of them. But let's say if n equals d, if I just trivialize all of these individual space-time directions, so like from this first case, if the number of directions I've trivialized is just equal to the number of space-time directions, this is called a topological twist. All of my space-time directions, all of my space-time translations become trivial in cohomology. If d is even, and equal to 2m. So I only have kind of the second type in play, nothing of the first type. This kind of twist is called the holomorphic twist. It's also often called the minimal twist. More generally, the output of the twist is something that we call a mixed holomorphic topological theory. If we have what I've written up here, where in general we have both of them in the game. So a twist will always give, twisted theories will always be one of these three types, either fully topological, fully holomorphic if the dimension is even and you can get away with that, or some combination of the directions will be topological and some will be holomorphic. That's the most general thing that can happen. So if we're thinking about twists in terms of simplified subsectors of the original theory, like in general, the most complicated and rich thing that we can deal with is our SUSY gauge theory or conformal field theory. But an interesting subsector of it, which simplifies it, but still gives interesting information, is the minimal or holomorphic twist of such a theory, if a holomorphic twist exists. And even simpler still is a more special type of twist that kind of lives at the bottom of the hierarchy. It's the simplest to study, but it has the least information associated with it, the topological twist. So that's how you can think of it. There are these hierarchies of twists. The holomorphic ones contain the most interesting information, but actually the mathematics associated to holomorphic theories is still being actively developed right now. But it should be very interesting for holography as well. Whereas the topological twists have been studied for a long time. They're the simplest. We kind of like the mathematics is very, very well understood. They're a bit simpler. I see some notifications in the chat. Any questions? I can also, let me just pause at this point for questions.
No, there's no questions on the chat.
Okay. So topological theories in particular, they're the simplest, and they actually typically satisfy an even stronger condition than all of their translations being trivialized. In general, the stress energy tensor of a topological theory is also Q of something, trivial in cohomology. For example, that happens in topological theories that have Lagrangians that you can write as Q of something, Q exact Lagrangians. I guess this can be, doesn't have to be the same something, but something. And so there are many examples of topological theories that arise from a supersymmetric twist where the Lagrangian can be written as Q of something for some chosen Q that trivializes all the space-time directions. And if you're in a situation like that, then it's kind of immediate that none of the correlation functions in a topological theory can depend on the space-time metric at all. It's really a completely topological theory at the level of cohomology. And that's just because if you remember that the stress energy tensor semi-classically is just defined as the variation of the metric, the action with respect to the metric, then if you look at the variation of any correlation function of Q-closed operators with respect to the metric, you get 0 immediately because you pull down something Q exact, and then you use the same arguments that I did before, where Q exactness in some correlation function means that you can pull the Q to act on everything, and you get a total derivative, and so it's 0 again. So topological theories really deserve their name in general. In our 2D 2,2 example, we had these three kinds of twists. We had the half twists, and we had the A and B twists. The half twist is a holomorphic twist of a 2D 2,2 theory. Meaning that correlation functions will only depend on insertions of the operators at various holomorphic coordinates, but they won't depend on any of the z-bars. And similarly, the OPE, say if we're doing a conformal theory, like if you're doing holography, the OPE of two operators is only going to depend meromorphically on the z-coordinates, not the z-bar at the level of this twist. That will give the operator product expansion of the algebra of local operators in a holomorphic twist in 2 dimensions, what's called a chiral algebra structure, something that only depends holomorphically or meromorphically on the z's, but not the z-bars. That's the kind of structure that governs the symmetry algebra of any conformal field theory, and it appears a lot. Just anytime you have kind of effective two-dimensional symmetry algebras, you'll have things of this type, and they can often be accessed somehow by a kind of holomorphic twist. So the half twist is sensitive to that kind of information. By contrast, the A and B twists are topological twists. They don't depend on any of the 2D underlying space-time directions. Now, so far I've said, okay, the twist is just purely the it's a cohomology problem. You just take the cohomology of the supercharge, you get some holomorphic or topological or mixed theory, and you study that. You study the operator product expansion, which simplifies because translations have been trivialized in some of the directions, and that has closer connections to math, and it's easier to study for various reasons. But again, it's capturing some kind of protected or BPS subsector of the original theory that you started with. But there is an important enrichment or caveat if you want to move beyond the flat space-times that I've been working with so far. And historically, this is often what people meant by a twist, this kind of extra piece of structure that I'm about to introduce to you, which is totally optional if you're working in flat space, but is important if you want to study these twists in more generality. So there's an extra ingredient that you can add if you're doing a twist. And this was introduced by Witten in his classic works, where he introduced a lot of this machinery. Kind of the formal name for it is a twisting homomorphism. Some extra structure that you need. Witten, also developed by many other people. And this kind of extra structure, which I'll explain shortly, comes about from asking whether or not your twisted theory could be placed on non-flat or non-trivial background manifolds. So if you want to do that, if you want to move beyond flat space, then this extra structure is often essential. But if you're content with working in flat space, you don't need to worry about it. So what is this extra bit of structure that's often added to these kinds of twisted theories? So in Euclidean signature, let's assume, so our theory, the theory that we started with, we're assuming that it has Lorentz symmetry, which in Euclidean signature is going to be spin D in D dimensions. Okay, so it's spin D in D-dimensional flat spacetime. Now, Q is some supercharge that we chose, but it transforms as a spinner under the spin D group. Certainly not invariant. It doesn't commute with all of the space-time rotations. And on flat space, that's okay. I don't care necessarily about preserving Lorentz invariance. Like a holomorphic theory is obviously privileging some of the space-time directions instead of some of the other directions. And that's okay with me because it's still giving me a very interesting, rich set of structure that's inherited from the original theory that I'm interested in studying. So in flat space, it's totally fine. But you might want to place these holomorphic or topological theories on more general manifolds. And there, because remember, manifolds are patched like patched together over like patches of spacetime that maybe locally look like RD or in complex dimension CD, but on the different patches, they have to be related by these transition functions that you glue together to make an interesting global manifold. And the transition functions involve, say, spin D transformations for Riemannian manifolds. And if Q is not commuting with those transformations that you need to build up the manifold, then the cohomology is not going to be compatible with putting your twisted theory on a non-trivial space-time manifold. And indeed, Witten was originally studying topological twists with this extra bit of data because he wanted to put topological theories like 4D Donaldson theory and 3D Simon's theory. You want to study those kinds of topological theories potentially on some interesting space-time manifolds. And in his case, he was interested in computing some geometric invariance. But even in physics, we know that it can be very interesting to study things on more general manifolds. And in particular, when you couple to gravity, that's essential. Okay, so how do you deal with the fact that the supercharge that you want to take the cohomology with doesn't actually commute with space-time transformation, with all the space-time rotations? So let me suppose that I'm working with a topological twist, meaning all of my space-time translations are trivial in cohomology. Then I can choose this extra piece of data called the twisting homomorphism. And that's defined as a map from my spin D group into my R symmetry group. So this is something I can typically do when I have extended supersymmetry. This map is injective, and it's what's called a group homomorphism, meaning it respects group multiplication. Like this, for any elements A and B in my spin D group. And we want to make some choice where we map this spin group into the R symmetry group such that Q transforms trivially, i.e., it becomes a scalar. So you basically are modifying all of the spins in your theory, and you modify them in such a way that Q, which used to be a spinner under the ordinary, the usual Lorentz group, now is a scalar under a new twisted Lorentz group, where you've twisted by the action of some of your R symmetry generators. So Q transforms trivially or as a scalar under a new spin D action, which is defined via this map. So I'm mapping spin D into spin D times GR. So under the first copy, it's just the identity, and it maps into GR via this choice of map that I've made. And again, I'll do an example in 2D shortly. So in other words, we're changing the spins of everything in the twisted theory so that there's a modified action of the Lorentz group that does commute with the action of Q. And once you've modified all the spins in this way, now for a topological twist, you can place it on arbitrary manifolds. So with this choice, a D equals N topologically twisted theory can live on an arbitrary background manifold. There are generalizations of this notion also to the holomorphic theories and to the holomorphic topological theories. The best we can do, though, of course, topological theories can be expected to live on arbitrary manifolds because for arbitrary manifolds, the patching functions are related by spin D transformations. For a holomorphic twist, the best you can do is put it on a general complex manifold. So there still needs to be a complex structure, and the transition functions are those holomorphic functions between different patches of your manifold. For a mixed holomorphic topological twist, the kinds of manifolds in general that you can hope to place these things on if you make this extra choice are what are called manifolds with a transverse holomorphic foliation, THF manifolds, which is a fancy name, but it just means theories, manifolds that locally look like some combination of real and complex directions, and the transition functions between two local patches, with the transition functions that remain holomorphic on the complex factors. So explicitly, if I have some x coordinates parameterizing Rn and some z and z bar coordinates parameterizing the complex directions, transition functions between patches can have arbitrary dependence in the R direction, but should maintain the holomorphicity of the complex directions. The generalization there is you can certainly choose another morphism, which I'll call I mix, which is the subgroup of the Lorentz group that preserves the splitting between real and complex directions, just depending on your twist. Could be all holomorphic, could be some split, but so this is just whatever subgroup of the Lorentz group preserves this kind of splitting. But again, you choose a map into whatever R symmetry group you have. Of course, this only works if your R symmetry group is non-anomalous. So for any given theory, you have to check the anomalies of the R symmetry and worry about that potentially. And that might restrict your options, but that's something that it goes on a theory by theory basis. So for example, if n equals 0 and m equals 1, the group that I called spin 0, 1 is just spin 2 or U1, just rotations of a single complex plane. If I have some three-dimensional theory that's like R across C, so n equals 1 and m equals 1, remember D is m plus 2m, then that group I would call spin 1, 1, which is just another U1 subgroup of spin 3. Spin 3 is like SU2. This is like a U1 inside of SU2. And again, it's just the subgroup of the Lorentz group that preserves the splitting between real and complex directions. So it's just the U1 symmetry that's rotating the complex plane around the real axis. So let me do an example of these twists in the 2, 2 theory, so you see how it works in a canonical example. So I'm about to get to the example, but I can pause for questions just for the understanding that maybe, hopefully I'm about to answer some of them, but does anyone have anything they'd like to ask in the meantime?
Okay, there seems to be one in the chat.
Uh-huh.
Do I expect topological twist to be defined in every manifold or just a spin manifolds?
Oh, good. There are possibilities to define topological twists on like non-orientable manifolds, for example. That involves some extra data, which I wasn't going to talk about today. The Kapustin-Witten paper, I think, has some remarks on that at the very beginning. They have a very large paper doing a topological twist of the Langlands theory, and they have some remarks about how you can choose some extra data, an additional bundle over the manifold, and twist by that to do to include orientation reversing possibilities. Again, it depends on the theory, so one has to be careful. But I believe it can be generalized. Does that answer the question? I guess anyone can like raise their hand if they want to ask a follow-up.
Yeah, it says thanks.
Any other questions? Okay, so let me do an example. What is this kind of morphism in the actual algebra that we've been working with? So we have our supercharges Q plus and Q bar plus. Our conventions is that those are defined such that they have spin 1/2 under spin 2. Spin 2 is basically U1 in 2 dimensions, pretty simple. And Q minus and Q bar minus under the Lorentz group have spin minus 1/2. And I'm going to call J the generator of this Lorentz U1. So for the A twist, let me remind you that QA was Q bar plus plus Q minus. And for the A twist, I'm going to twist by the vector R symmetry group. So Q bar plus Q minus has the following symmetries under R vector and under this rotation J. Q bar plus has -1 and 1/2, and Q minus has +1 and -1/2 from my definitions earlier. So the twisted action of the Lorentz group that I want to define is just J plus 1/2 RV. And if I make that definition, then it's immediate that this twisted action of my Lorentz group, twisted U1, does indeed act trivially on the A twist. So now I could take my 2D topological A-twisted theory and place it on an arbitrary 2-dimensional manifold. And this occurs, for example, if you want to couple an A twist of a supersymmetric field theory to 2-dimensional gravity and make a little 2D string theory. So you might want to sum over all Riemann surfaces. But more generally, it's just a 2D field theory, it's topological. And now, because the supercharge commutes with the twisted Lorentz group, you can just define it on any Riemann surface you want. There's a similar thing you can do for the B twist. Remember QB was Q bar plus Q bar minus. And there the right definition is to use that axial U1. And indeed with the definitions, you check that it does the right thing. So these two topological theories indeed can be placed on arbitrary two-dimensional Riemann surfaces if you make this additional choice of twisting morphism, mixing the spins of everything up in particular so that your chosen supercharge is a scalar under your twisted Lorentz group. This notion could also be generalized to include other internal symmetries. Say if I have some other internal symmetry group H, if it commutes with the R symmetry and Lorentz groups, then you can further enrich the twist or make a modification of the twist with, say, a map from spin D into GR cross H. So again, modifying spin D compatible with the twist, but if there's other internal symmetries, you can use those two in principle, but I won't really talk about those today, just so that you know it's in principle possible. So for most of the rest of the lectures, I'll just want to work on Euclidean signature flat space and not make such a choice of twisting morphism. Indeed, a lot of the work on twisted holography is at that level. So certainly that's already an interesting thing to do even before you make these additional choices. It's very convenient. And again, I want to stress that if you work in flat space, this choice of the twisting morphism is optional. Although, like back in the olden days when people were talking about twists, they always implicitly included this choice because they were really interested on working on all kinds of manifolds. But on flat space, it's optional because in flat space, we don't have to worry about the action of Q being compatible with changes of coordinates on these non-trivial manifolds. Another way to think about what I've just done is the physics words that you can put around everything I've just said, which are totally equivalent to the math words, are that I've turned on a background R symmetry bundle to cancel the effect on Q of having a non-trivial spin structure on space-time. So I've turned on a background R symmetry bundle to cancel the effect on Q of the space-time spin structure. And again, for this lecture, I'm working in field theory, so these are all non-dynamical backgrounds that I'm turning. Okay. Let's see. Let me make some quick remarks, including one that's relevant to one of the questions from earlier. So remarks. In general, I could study some SUSY QFT, as was asked about, in the BRST quantization, which we reviewed at the beginning of the lecture, and as well, I could consider the supersymmetric twist of this thing in the BRST quantization. In general, a SUSY quantum field theory in the BRST quantization has two natural conserved quantum numbers, which mathematically we call gradings. But just two quantum numbers, which means that I can take my big extended field space before I even take the cohomology and consider it as being labeled by these two quantum numbers that I'll call little n and f. Little n is an integer, and f, which is fermion parity, is just something defined mod 2. So f is fermion parity. We certainly have that in a SUSY QFT. And n in BRST quantization, which you've probably seen when you've studied BRST quantization, is the ghost number, where the C ghost has ghost number 1 and the B ghost has -1. And under these two quantum numbers, the original BRST differential, I called it QB before, but let me just call it D now. Under these two things, it has ghost number 1 and fermion parity negative because it's anti-commuting. A twisting supercharge, if I wanted to take this BRST quantized gauge theory and then twist it, that has ghost number 0 and also negative fermion parity. So if one really wants to do a twist of a BRST quantized theory, more properly, we're really doing cohomology with respect to a sum of the two supercharges, the BRST differential and the twisting supercharge. To first approximation, you can usually just think of these things as gauge invariant operators that are also BPS with respect to that supercharge, although that's not quite true. And there's a mathematical way to properly commute cohomologies of these sums of things. It's what's called the spectral sequence problem, but I'm not going to talk about that today. And in practice, you often don't have to worry about these technical subtleties, but just good to keep in mind if you run into exotic counterexamples from time to time. So if I'm really taking the cohomology with respect to the sum of two things, the only quantum number they have in common is fermion parity. They both have this minus sign. So after the twist, only the grading by fermion parity survives. Because ghost number is not compatible with this sum of the two differentials. But if it's often convenient, more quantum numbers is always more convenient to work with. And typically you can do a little bit better. Anytime you have non-minimal supersymmetry, you can typically use the R symmetry to do kind of a further modification and get back an extra integer quantum number even after the twist. And this is often also a very useful and a very common thing to do. And you'll see people use this trick in the twisted holography literature a lot as well. So if you have non-minimal SUSY, you can use the R symmetry to do a little better. Again, I'll just choose a map from U1 because I just want some integer quantum number into my R symmetry group. Again, the U1, whatever thing I'm twisting with has to be non-anomalous. But I want to choose some U1 subgroup of my R symmetry group such that Q has charge +1 under this U1 symmetry, and also so that it's compatible with fermion parity. -1 to the fermion number, I want it to be equal to -1 to the R symmetry number. I'm going to call this U1 the R charge, this chosen U1. Obviously here I've assumed that the theory only has integer R charges. Not every theory that you encounter has this, so you can't always necessarily make this choice. But if you're in that situation, then you have an extra U1 grading or U1 quantum number by this gamma, which is called the R charge. And then the twisted theory gets a surviving integer grading, which is often called the cohomological grading. That's the sum of the ordinary BRST ghost number plus this extra R charge. So you can still get an integer grading if you make this little extra choice. And this cohomological grading also determines fermion parity for free because I've chosen this R charge to be compatible with fermion parity already. And moreover, ghost number is also correlated with fermion parity already because the ghosts are fermionic. A C ghost also has something of odd ghost number also has that fermionic parity. So I can also get fermion parity there because ghost numbers are related to fermions. So this is useful because the twisted theory now has an extra quantum number. So conventionally in the A twist, the cohomological grading is usually taken to be the ghost number minus the axial R symmetry. So I used in the A twist, I use the vector R symmetry to modify the spin and make things scalar. But in 2D, things are really convenient. I have two U1s in the game. As long as they're non-anomalous in the theory that I'm interested in, I can use the one left over. In the case of the A twist, is the axial symmetry to modify the differential and preserve an additional quantum number, an additional U1. And in the B twist, it's ghost number minus RV. All right. So that's some enrichment that is often convenient and people can and do use it. All of that was twisting supersymmetric field theories. And I'm just going to say some stuff in words. Here, I can't be fully pedagogical. Twisting supergravity is a much more subtle prospect than twisting a field theory. Of course, for twisted holography, you'd really want to do both. But in twisting supergravity, supersymmetries are gauged. And so you have to figure out what twisting a gravitational theory means. And there are various proposals for what it means, although they're not background independent proposals. Typically, you need particular supergravity backgrounds in order to have the proposal make sense in the first place. Backgrounds with some extra symmetry and with some nice asymptotic boundaries. So again, the conjecture for what it means to twist supergravity, you can read more about in the paper of Costello and Lee. There's also proposals for localization by Murthy, DeWitt, and Reyes, and related works at the level of indices and partition functions by Gentilini, Gauntlet Sparks, and others, I'm sure. And the idea is that you take a lot of the ingredients in the twist, but at the level of classical supergravity data instead, and try to modify it in some way. So in classical supergravity, I would have some choice of space-time manifold sigma with some metric. I would have a spin bundle, a dynamical in general spin bundle, an R symmetry bundle over those manifolds. And those bundles will also have connections associated to them, giving me the fluctuating supergravity fields. And so instead of choosing a nilpotent supercharge like we do in field theory, the idea is that in a supergravity twist instead, you turn on a vacuum expectation value of a ghost field, the ghost field associated to the chosen super translations in the supergravity algebra. So we have fermionic ghosts for bosonic symmetries like gauge symmetries. For supersymmetries, there are also ghosts associated to those transformations, but they take the form of bosonic ghosts. The proper thing, and when you have gravity, you really have to work in this big BV-BRST formalism that I mentioned, but don't have time to really explain. That's essentially the proposal. And then other ingredients like the twisting homomorphism and this map gamma all have their own kind of conjectural versions in gravity, where basically you're now choosing appropriate bundles and connections over your space-time that kind of have properties that you want. But again, it's a little bit too much to go into all of the details. You can read more about it in this paper. But all of the things in supergravity have kind of analogs at the level of this geometric data. But it's certainly more conjectural. And in fact, the main conjecture of Costello and Lee, which is most useful in twisted holography and often the most interesting, one that we've used a lot in examples, is that there exists a holomorphic twist of type 2b supergravity. At least on 10D flat spacetime. More generally, you can actually define it on a Calabi-Yau manifold if you want. And that's associated with a particular choice of bosonic ghost. So the claim is that such a thing always exists. Since I haven't written down the supergravity, I won't tell you too many details about the ghosts, but I think the best way to think about this kind of twist is as follows. If, let's say, you have any field theory, so we've talked about twisted field theories, and they're more comfortable objects. If you have some field theory that can be coupled to supergravity, and you should think of, say, the world volume theory of some brane in type 2b string theory, then putting this supergravity theory in this unusual vacuum, where you've given the bosonic ghost some vev, will induce on the world volume of that brane or on that field theory the corresponding holomorphic twist on the field theory. In other words, you will induce an ordinary field theory twist, like the ones we've just been talking about, by a unique, up to R symmetry unique, SU5 invariant supercharge. And again, at the level of field theory classifications, you can check that the supercharge exists and is SU5. So, Q, this bosonic ghost field Q, is set to some value corresponding to a covariantly constant spinner for the chosen space-time metric. In this case, in flat space, it's some very simple thing. We know it exists. We can certainly find covariantly constant spinners in flat spacetimes. You can generalize it a bit to other spacetimes, and that will induce some ordinary nilpotent supercharge on the world volume theory of any brane that's coupled to this thing. So again, it's best studied in BV-BRST formalism if you really want to see all the details. And there's like classic lectures by Hainaut of BV-BRST formalism and why you need it and what it's good for. And the idea is you're extending your space of fields a lot, just like you do in BRST formalism. You write down this fully BV-BRST extended action. One of the fields, this bosonic ghost, gets a VEV. And that will mass up a lot of the other fields in the BV formalism. So you can integrate out all these kinds of massive fields where they get masses just from coupling to this one bosonic ghost that gets a VEV. And you can reduce something like a 2B supergravity action to something simpler. Of course, doing this in full generality and in particular on more general backgrounds is very hard. Although again, in flat space, we do have partial proofs of this to some extent. In general, supergravity off-shell stuff, it's hard to do in full generality, but at least in flat space and with a bit of hard work and some examples, such a twist of type 2B supergravity reduces to an action, which is called the Kodaira-Spencer theory of gravity. This is like a holomorphic analog of a gravitational theory. You can even derive terms in the action of Kodaira-Spencer theory from this procedure that I just mentioned. You have supergravity in the BV formalism, you give some field of VEV, you integrate stuff out, and something simpler pops out. And it's a gravitational theory in the sense that it doesn't remember all of the dynamical components of the space-time metric or all of the fields that you had in the original theory, but it remembers some subset. It's some subsector of the original thing. And in particular, it's a kind of holomorphic analog of supergravity, just like the twists that we've been studying are like holomorphic, simple holomorphic field theories. The original paper that studies this is by Bershadsky, Ciccati, Oguri, and Vafa. So it's also called BCOV theory sometimes, if you want to read more about how this theory is actually defined. And it's also discussed extensively in a gigantic book by many authors called the Mirror Symmetry book. And so you can read more about these kinds of things as well. So what this Kodaira-Spencer theory is, it's actually the space-time low energy effective theory associated to the B model topological string. So actually a string whose world volume theory has undergone this B twist that we've been talking about. And the branes have world volume theories that are holomorphic field theories. They're holomorphically twisted. And in the B model, they're called B branes. And let me emphasize the following thing, because this terminology confuses people a lot. I've used these words B model topological string. So conjecturally, they're defining a twist of my space-time supergravity theory, at least on flat space. So to get a B model topological string, you have to do a B-type topological twist on the world sheet. That's what I was talking about. The correlation functions of a 2D 2,2 theory after the B twist do not depend on the two-dimensional metric. So it is a topological field theory in 2 dimensions, the world sheet theory. In other words, the world sheet metric is QB exact. But the space-time theory that you get out is not topological. It is holomorphic. It is more interesting than some kind of topological version of gravity. In fact, it's a richer thing. It's holomorphic, and it retains dependence on some components of the metric in space-time, although not on the world sheet. The particular metric components that it remembers are what are called complex structure deformations. Roughly speaking, there's some pieces of the metric that deform like the shape of a complex manifold, but don't remember anything about the size of a complex manifold. So the terminology causes a lot of confusion because topological strings, topological B model, it sounds like you're just getting some topological bulk space-time theory, but it's only the world sheet that's topological. The space-time theory is like a holomorphic gravity theory. And that's important to remember, and that's why twisted holography is interesting. So just to kind of give you kind of the interesting punchline, twisted holography, why I use all of this machinery. Twisted holography is holography for this twisted or topological string type setup. In other words, so normally, as you learned about in ADS-CFT, you start with like type 2b string theory or supergravity on flat spacetime in Euclidean signature on 10 dimensions. You add a bunch of D3 branes, which source some Ramon-Ramon flux, and they back react, and you take these limits and you get ADS-CFT duality. And at 4D equals 4 super Yang Mills lived on the world volume theory of those D3 branes. So you back react and take some limits, as you guys probably learned, and you get the ADS-CFT duality, 5 and 4 in that case. Twisted holography is the same thing, essentially. Morally, it's the same thing. Start with the Kodaira-Spencer theory, this holomorphic gravity theory, and add n B branes and back react. So the B branes also source, so there's some like holomorphic remnant of the Ramon-Ramon field that the B branes source, and it deforms the complex structure of the metric rather than the full metric, because that's all that remains in the twist. And you get some twisted ADS-CFT duality. Although exactly what you get out depends on various details. But the idea is really the exact same. So you deform only in this holomorphic land, you deform only the complex structure of the metric, using whatever piece of the Ramon-Ramon flux survives the twist, whichever component survives. And you get a complex manifold out. And similarly, the world volume theory on these B branes is some kind of holomorphically twisted theory. So the OPEs depend on the holomorphic coordinates, and you restrict to some simpler algebraic subsector of, again, whatever theory you were interested in, whatever. For more details on some of the matching between these quantities and in examples, I wrote a recent paper with my student Victor Fernandez and also Brian Williams that's based on an earlier paper I wrote with Costello, where we do this in detail for an ADS3 CFT2 duality. And in the first section of the paper, or the second section or whatever, we take some extra time matching physical fields with, what do they produce in the Kodaira-Spencer theory after the twist? How do some of these things match up with one another? And then we study also the boundary, the holomorphic twist of the boundary 2D CFT. So this is like a half twist here and a Kodaira-Spencer theory here. And so we flesh that out more in a particular example. And we even use the setup to compute planar OPEs of what in the original physical theory were quarter BPS operators, but are just some, again, holomorphic operators in the twisted theory. More generally, there's other twists you can do in many other examples, and they're interesting in holography in various contexts. For example, the holomorphic twist of 4D n equals 4 is sensitive to what are called 16th BPS states, which is believed to include black hole states. And that's also now a very active area of study, trying to understand these mysterious states, which are computed by some supersymmetric index and seem to be accessible from the holomorphic twist. But how to compute these things at finite n and match them in the bulk is a very active area of study by many people currently. And I can't give a complete list, but Chang, Lin, and O have a nice paper connecting these states to the holomorphic twist. Budzig and Vieira et al. Also have some interesting work on it, and so on. So there's a lot of, and there's other authors too. So there's a lot of active work on these twists, capturing supersymmetric observables in holography. Okay, so I think that's a good stopping point for what I wanted to say in these lectures. Of course, I had, in principle, like 10 more pages of stuff that I could talk about, but it's all in the TASI lectures too. And yeah, happy to take questions at this point.